So the second part of this lecture will go over the transfer matrix method. And I am actually quite excited about teaching you this, although it will involve quite a lot of math that we have to go through. But the reason why I'm excited is because this method actually has a lot of applications. So on one hand, I showed this dielectric filter. Unfortunately, it's not a video in the PDF here in Canvas conference. But if you open, for example, the PowerPoint that I put on the canvas, or if you just also look at this here a little bit, dielectric filters can be quite interesting because you can, for example, have here a situation where the transmitted light is blue, but the reflected light, you can see it here a little bit, is yellow. And you can get here the complementary colors again from these dielectric filters, whether you look at transmission or at reflection. And if you tilt it a little bit, you will get even different colors. And in fact, I use this method a lot in my research for solar cells. So for example, for optimizing anti-reflection coatings for the solar cells, but also actually quite a lot of other things where you want to optimize the optical properties of the solar cell. And originally, I was planning to show you this before the break, but because that didn't quite work out, we're doing it now. I hope we'll have enough time for everything in this lecture. But I wanted to show you a little bit example master projects in which this method actually came in quite handy, and also the knowledge of this method came in quite handy, namely Lisanne Einhaus, who took this wave optics class in 2019, and Gert Harris, who took the wave optics class in 2020. They have both been doing their master project on a project which we call free space concentration of diffused light. And so why are we doing this? Well, the idea is that we want to design materials that we can, for example, put here on the facades of houses or in between solar cells. And then these materials can capture light from a lot of different angles and a lot of different wavelengths, and then emit the light in free space towards the solar cells with a down-converted energy of the photons, so going from, for example, blue photons to red photons. And so we get then extra light on our solar panels and can concentrate diffused light, so light coming from all directions directly on our solar panels. And that's normally not possible. And so with this project here, we try to make this possible. And transfer matrix method actually plays quite an important role for this. And I want to explain this to you a little bit why before we actually go into the process. Well, normally it's not possible to collimate or to direct diffused light into a certain direction. You can think about it from a very basic thermodynamic principle, namely if you have light coming in under a lot of directions, if you now want this light to suddenly be collimated and only go into one direction, what you would do is you would destroy entropy in the process. And that's of course not allowed. The only way this could be allowed is if in the process you sacrifice energy. And the way we're doing is the following. So we want this situation where we take in a lot of light from different angles, and we then emit it under a very specific angle. And in order to not beat thermodynamics or do something that's thermodynamically not allowed, what we're doing is we're taking so-called luminophores. These are fluorescent nanoparticles, can for example be a dye or a quantum dot. And what they're doing is they absorb light under with a higher energy, so higher photon energy, and then they emit light with a lower photon energy. So for example, they absorb blue light and then emit red light. And then we do something which we call the nanophotonic emission control. And this is basically what you're learning here in this lecture, is how such nanophotonic concepts work. And by using different nanophotonic concepts, either plasmonic or photonic crystals or dielectric thin film stacks, that's the part we're talking about today, we can now design the surface properties in order to only allow light out from a different angle. And so the idea is now that we are making something that's called a luminescent solar concentrator. So we have a situation here where we have a waveguide. You guys already know roughly what a waveguide is. So we have a waveguide here. We have these luminophores inside our waveguide that absorb light and then emit the redshifted light. And normally what people do is they put then a tiny solar cell here at the edges and use a nanophotonic thin film coating, so a dielectric thin film stack here, in order to make sure that the light that is emitted here cannot go out, but that it will travel to the solar cell. However, there are a lot of losses here involved, and that's why this technology hasn't really had any breakthrough yet. And so that's why I had the idea, let's do the following. Let's design this nanophotonic thin film coating here in order to keep light in if it's not in the emission cone that we want, but let light out if it is in the emission cone that we want. So that means that we want to design a surface. So in this case, they are trying to design surfaces that have zero reflectance for a certain photon energy or a certain photon wavelength regime. So they can let all light in under all wavelengths and all angles, and then keep all light inside the waveguide for the redshifted light. So for lighter wavelengths, they want then to keep all the light inside the waveguide. And now in our structure, what we want to do is we want to design this nanophotonic surface coating that it also lets all light in from all angles and all wavelengths until a certain wavelength. And then the light that is then emitted under a higher wavelength, the lower photon energy, will stay inside. If it is, that's unfortunately a little bit small here, if the angle of this light is larger than what we want the light to allow to go out, and it is 0, so the light can go out under a narrow angle. And so that's what we are designing for, to make to make a material that can allow this, that the light will only go out under a narrow angle, and thereby we can achieve free space diffused light concentration. That's the first, in my opinion, or as far as I know, the first method with which it could be achieved, that we have that we take diffused light and can concentrate it in free space. And so in order to achieve this, what now Lisanne did is that she used such a thin film dielectric stack containing of layers of silicon nitride and silicon oxide. And she used now the transfer matrix method in order to calculate the angle and wavelength dependent reflectivity of such a stack. And in fact, she did not only calculate it, but she then also came up with the idea to use a particle swarm algorithm in order to optimize the thicknesses. And then she came up here with this situation where you have different thin film materials on top of each other, all very thin. Here the layer thickness is in the order of like 90 to 160 nanometers. And so she optimized the layer thicknesses of the stack and then calculated with transfer matrix method what are now the optical properties of such a surface. And not only did she calculate it, she also made these in the lab, and then she measured the reflectance of such a structure and the transmittance of a structure and compared it with her simulation. And the cool thing now is that in fact they matched really well. So you can in blue see the simulation, that what she calculated, and in red the we call it here the MEMPEX, that was the name of the sample. In red you can see the measurement, and there's a really good correlation between what she calculated and what she then fabricated and measured in the lab. And you can see it here also under if you just look at it with just with your eye, you can see how this light that is reflected under a shallow angle looks red, and then blue light is just transmitted. So even with what my former mentor always used to call eyeball spectroscopy, so just by looking at it, we can already see that it does roughly what it's supposed to do, but then there's also really good quantitative agreement between what you simulated with the transfer matrix method and what you then measured. And so that's why I really like doing optical simulations, is because it's very satisfying to then later see in the lab that the stuff actually worked, and you calculated something that then you can really also obtain in the lab. And so now what Geert is now working on is, or what he then did, is he then took this first of all, he changed the color spectrum. So now we have different colors here, so don't be surprised about this. But we're still looking here at the angle and wavelength dependent reflectivity or reflectance of such a nanophotonic surface. And then he put the emission of the luminophores, he included that, and then he performed what we call detailed balance calculations to then figure out, okay, if I have such a nanophotonic surface coating and I have such an emission spectrum of my luminophores, what is then the angle and wavelength dependent emission that I can get from such a material stack? And in fact, so that's shown here, in fact, we can get a very nice situation where we have really good concentration and a certain emission angle for the specific wavelength at which our luminophores are emitting. And so he calculated this. This is really great work, which we are currently also putting in a paper. And so at the moment, he's busy actually demonstrating this in the lab. So he's mixing luminophores and putting it together with this nanophotonic surfaces to see whether we can actually achieve these properties that we're looking for in the lab. And I only wanted to give this example a little bit as a teaser so that you can see that this method, or also what we're learning here, is then actually quite useful when you're doing your master research and later maybe also your PhD research in the lab or in the groups. And it can also be very helpful in order to design certain optical elements, because most of the time, if you do everything correct and use the right material input parameters, you can actually reproduce what you calculated on your computer. You can actually get those properties in the lab as well. And calculating is much faster than making it. You might think calculating is difficult, but I can tell you making stuff is even more difficult. So that's why we really always try to calculate things first. So that's a little bit of a motivation why I find this method really cool and why it can be really helpful. And so now let's actually look into how this method works. So the principle of these, for example, anti-reflection coatings, color filters, or thin film, multi-layer thin film stacks, in principle, or in general, is the following. We have light coming in, and this light will now bounce off or will partially be reflected at the first interface, but then it will also be partially transmitted. And then here at the second interface, we will have the same phenomenon again. There will be a partial reflection and a partial transmission. Out of this partially reflected light at this first interface, there will be partial transmission, which will be this ray 1, and partial reflection. Then, again, here at this interface, there will be partial transmission, partial reflection, and you can see where this is going towards, right? So this is basically going into an infinite loop. We will have infinite options for this light coming in and being partially reflected, partially transmitted. And then, of course, if I add even more layers, then you will get even more effect from partially transmitted, partially reflected light from even more layers. And that's what we want to deal with. And one thing I can already tell you, there are other ways than the transfer matrix method to deal with this as well. The nice thing is that these are reflections here are decreasing. So, and it's of course a value smaller than 1. So very often you can solve such a problem also with a geometric series that is actually converging. So that's very often if you only have, for example, one layer or only one particular one material in your stack, very often I solve it also with a converging geometric series. However, what we're looking at today is how we solve this in this matrix formalism. And how we do this is somewhat similar to how we derive the Fresnel equations. And just as a reminder, Fresnel equations we derived from knowing Maxwell's equations. Maxwell's equations should be familiar for all of you, and I'm pretty sure that Peter also reminded you of them. I think also did in the first lecture. So I'm not going through them, but from the Maxwell equations, of course, on one hand, we can derive that electromagnetic waves exist in vacuum. So when we assume homogeneous and isotopic media without external sources, we were able to derive here these wave equations for the electric field and the magnetic field. And we were able to derive that then epsilon 0 times mu 0 corresponds to 1 over the square of the vacuum velocity. And we were also we also then introduced the refractive index and how it then how it can be expressed then by the by epsilon r. So these were the things that should already be familiar to you. And if you now think back to your bachelor optics class where we derived the Fresnel equations, then you hopefully remember that what we had to do in order to derive those were two major things. So first of all, we had to look into the boundary conditions at the interface. So what happens to the electric field and to the magnetic field once the light hits basically the interface, or once the light wants to propagate from one material into another. So we need to make sure that these boundary conditions at the interface are met. So that's what we also had to do for Fresnel equations. And then we figured out from there that, or from Maxwell equations that tell us that the tangential components of the E field and the H field are continuous. So that's important for also our later derivations, and that was also important for deriving Fresnel equations. And the other thing that was very important is that we considered certain polarizations. So we split up our wave that came in into TE, so transverse electric polarization, and TM, transverse magnetic polarization. So what does that mean? If we think about such a situation where we have, for example, air or vacuum, and then a material with refractive index N1, then all our ray that's coming in, our refracted ray and our transmitted ray will be in one plane. We call this the plane of incidence. And so now our electric field vector can be split up into one component that will be within this plane, so it will be parallel to this plane or in this plane, and a component that will be perpendicular or transverse to this plane. And if we talk about TE, then we mean that the electric field component of our electric magnetic wave is transverse, so perpendicular to this plane of incidence. And so that's called TE, and it's shown here by this cross. That just means, okay, it's going inside our plane. And we also call this S polarization. S is from German senkrecht, which means perpendicular. And on the other hand, the other part would be then TM polarization. For today's lecture, we're only working through the math for TE polarization. TM is slightly different, but equivalent, so we will not explicitly look through the math for that. Okay, and then also not going in detail through this because you did that in your bachelor course already. But if we then consider this fact, or like consider the fact that we have either TE, I just explained what this is namely the wave vector is perpendicular to the plane of incidence, which is shown here in gray. We arrive at the following equation for the reflectance of a certain surface. And for the p-polarized light, so TM or parallel p-polarized light, we arrive here at this expression for the reflectance of the surface. Okay, and so now we are briefly remembering about another concept as well, which you already learned during your bachelor's, which was the ray transfer matrix analysis. If you think back, what was possible is that you can calculate what the effect of an optical system is by using the ray that you had in the beginning. So the incoming ray, you defined the location and the angle, and then you can define for each optical element, you can define a certain matrix. And this matrix is then acting on your incoming ray in a certain way, and such that you then will get a certain outgoing ray, which is again defined by location and an angle. And now the very nice thing about this is that you can now just add different objects, or like you can now, if you have a more complex optical system that doesn't only consist of one lens, but maybe multiple lenses and other optical components, you can mathematically express this by having now a product of all these different matrices of the optical elements. So you can just easily insert or just plug it in and then calculate what the overall factors of your optical system. So that's quite convenient. And now we want to achieve the same thing. So now we want to be able to describe our multi-layer system that we have with a matrix formalism, such that we can be able to just insert for each layer a new matrix and do not have to come up with an analytical solution for each new case, but we can just say in this matrix formalism, each layer will be represented by its own matrix. So that's our goal that we are looking for with the transfer matrix formalism. And in order to get there, now again, we have to look at the boundary conditions that we get at the interface. So that's again our starting point to derive this formalism. And I already mentioned we're only looking at TE polarization. So now the tangential components of the E and the H field, it should be here, are continuous. And because that is the case, we can set up certain equations. And so now there is a, let's say, there's a certain elegance in the equations that we set up. Namely, we are trying to now, what we're doing now is we're trying to connect this interface, so the first interface, to the second interface. So we're trying to come up with equations where then at the end we can express what the fields look like at the first interface by the fields that were existent at the second interface. So we're connecting these interfaces with each other, and we're doing this in a way where we do not need any information about the material that's here outside of this layer that we're currently concerned with. And that's very important, because that will then later on enable us to just plug and play like the different matrices for the different layers. Okay, concretely, what are we doing? So we are expressing the electric field here at our interface. I call it now 0 here because it's E0. We are expressing this as the electric fields that are coming in on this interface or that are going out on this interface. So on one hand, we have this ET1, and ET1 is the electric field associated with the light that is transmitted into this layer. And on the other hand, we have ES1, and ES1 is now the electric fields that are associated with light that is coming towards this layer. So that is hitting this interface, I should say, sorry, hitting this interface here from this direction. And what is now very important is that this ET and ES is not just the first order. So it's not just, okay, light comes in and goes through, and we're considering it here, but it actually sums up all the higher order effects as well. So in this T1, it is also included that then here we will have partial reflection again. So this component that I didn't draw here now, but that would also actually exist in reality, partial reflection down again, and then also even higher order. Again, this is all lumped up into this ET1. And the same for this ES1. So it's really including all order reflections or transmissions. So it's all including really the sum of all order components. That's important. Then we can do the same thing so we can set up this equation for the electric field. We can set up the same for the magnetic field. The only difference is that now we are getting this cosine component here because of the effect that we're not having the full component here at the interface, but only the cosine component will stay continuous. And so that's why, in order to meet this boundary conditions, we only have to look at the component that will be parallel to the surface, and that's where this cosine component here comes in. The reason why also the refractive index now comes in is because that then will, of course, tell us also the angle under which we go in. So that's something we would then obtain from Snell's law, is the angle that we will then actually have in our material. And so that's where then also the refractive index of this material here comes in. And then we can actually do the exact same thing then for this bottom surface or bottom interface. So this equation here, E1, is completely equivalent to this first equation. So third equation is completely equivalent. We're saying the electric fields now present on the inside here of this E1 interface correspond to the sum of EI1 plus ER1. And again, EI1 is really all the sum of all the also higher order effect lights that are coming, higher order rays that are coming in from the top to this surface, and the same here for ER1. This is also summing up of all the higher order rays as well that are going away from the surface. So this is how we can set up our equation for the two interfaces, and then again for, I will not explain again because it's exactly equivalent to 2, only for this bottom interface. And then 5 and 6 are different, namely in 5 and 6, we are now connecting the first interface to the second interface, or let's say we are connecting the fields here at the first to the second, namely by saying that EI1, so the field that we get here from the light that's going down to this bottom interface, equals the field that left the top surface and went down, which is ET1, times now this phase effect here, which is E to the power of minus I D1 K1. So D1 is the thickness that we have here. Actually, no, it's the length that the light travels. And the reason why now this phase effect is important is because we are always talking about coherent light in this system. So whenever we talk about transfer matrix, we are always assuming that we have coherent light, so that the phase relations stay constant. So that means that this term here will now give us the phase relation between the light here and the light here. Well, and why is this important? Well, because that will, of course, then tell us if, for example, our surface or our thin film that we are creating here will lead to constructive or to destructive interference. So keep in mind that these are basically the terms that tell us this, this whole phase relation, and that are very important, and that these only, tell us basically what's happening, or having this proper phase relation here is then only possible if we really work with coherent light. Furthermore, in these expressions, you can also add if there is any absorption. So you would also add this here, that the amplitude would decrease over the course of traveling through the material. So that would also be included here, both in this equation 5 and 6. Okay, and so as the next step, what I then did is, okay, we have our 6 equations. What we want to do now is we want to achieve a situation where we have E0 expressed by E1 and B1, and B0 also expressed by E1 and B1. And that is really then how we would connect the interfaces of the two from like one side of the layer and the other side of the layer. And we have these 6 equations which make it possible. And what I then do is I translate these in slightly easier equations so that I do not have to write everything here, like all these cosines and everything out explicitly. So that's why I made this a little bit easier and introduced new parameters. Maybe it's not easier for you. This is just a way, it was easier for me to do this on paper. So that's how I'm explaining it now to you. Of course, you could also just continue working with all these original parameters so that you still know what you're actually doing. But I translated it into an easier looking system of equations. And now what we want to do, we want to eliminate variables b, c, f, and g, and we want to express a and d as a function of e and h in these like new substituted functions. And well, now this is all algebra, like very simple algebra, to be honest with you. So I will not go through this in detail. If there's a question about it, let me know. But so we are now, as I said, we eliminated all the parts that we didn't want and expressed now a and d as a function of E and H. And then we get the following expression here for A. We get here E plus H divided by 2, and then we get this E to the power of IX term. And then we get this term here, and then with we can, of course, write this like this. And now we can use Euler relation to express the E to the power of IX by cosine and by sine functions. And that then actually leads to a really simple equation. Then suddenly A can be expressed as E times cosine X plus H times I sine X, and D can be expressed as E times I sine X plus H cosine X. And now the nice thing is we can now write this in matrix form. So now we can say we write this in a matrix form where we have this vector AD and this vector EH, and we can use this matrix here to reproduce exactly this solution or this equation system here that we derived. So now if you look at multiplying here in this matrix, you would for A, you would receive A equals cosine E times I sine XH. That's exactly what we had here. And D equals I sine X times E plus cosine X times H, which is exactly the bottom part here of this equation. So that's how we arrive here at this matrix form for the equation. And now we can substitute everything back, and this is now the reason why I used A's and B's to make this a little bit easier to understand how we arrive at the matrix, because this is now, of course, a little bit more, there are significantly more parameters here, but this is really just substituting back from my funny A, B, C, D, E, F, G notation back to the original notation where we use the E field, EH, refractive index is what I lumped all of this up, even the angle, the cosine alpha 1, I also lumped this up into my substitution. And so substituting back, we are now achieving we are now obtaining here this matrix equation for our TE polarized light. And then TM we didn't explicitly talk about, but this is how the TM expression would look like. And so now, just to make this clear again, what are we doing now? So we have here our E0 and and B0. So we have here our top surface, and we have our bottom surface, and then we have this matrix that is only dependent on properties of this material, of this thin film material, that is now connecting the fields of the back surface, of the bottom surface, with the front surface. So that's now what this formalism is doing. And now what's so convenient about this is now we can really, if we have a multi-layer stack, now we can just add matrices to it. So each layer in our stack will now just correspond to an additional matrix where, again, basically the parameter that goes in is mainly here this refractive index. That's really the important, of course, the important characterizing optical parameter of a certain material. And so now that's very convenient. We can just add matrix by matrix for each of the layers that we are that we have in our stack. And after you have done this, so we will not derive this here, but it's being derived the exact same way as we derived the other parts. So now we can then come up with an equation for our reflection and our transmission. And so now what's very convenient is that what we can do is we can multiply all these matrices such that at the end, we end up with one matrix again. And in order now to calculate our reflection and our transmission through the surface, we just take this final matrix that we got out, and we take the matrix elements and put this into this equation for reflection and transmission. And so really, we calculate for all the different layers, we calculate what is the final matrix, and then we take the matrix elements M11, M12, M21, M22, put it into this equation, and can calculate the reflection and the transmission. And as I said, we won't derive it here. You can, for example, do a sanity check by comparing it with Fresnel equations for example, one case. You can think about how you could do that. I'm not going to tell you here because that's something I think that's nice to discuss it in order to understand this a little bit better amongst your study groups. But and if you have no clue, of course, ask me. But what you just one comment is, of course, you would calculate here the reflectivity by or reflection by dividing the reflected field by the incoming field. So that's how you would do that. And again, you would have to take the different boundary conditions in order to arrive here at this equation. For now, this is just in order to show you that this is the final equation, and you could use that in order to calculate your multi-layer stack. This whole thing also works for absorption. So absorption means that you have to use the complex refractive index and you have to plug this in. And then again, something that you can discuss in your study groups, but you can also ask me if you cannot arrive at the solution, is how could one then calculate the absorption of a full stack or of one specific layer? So how would you calculate this? What are ideas how you could do this with this formalism? Okay, one thing. Yeah, okay, let me briefly summarize how the transfer matrix method works. So if we want to use the transfer matrix method in order to calculate a multi-layer stack, the way we derive this method is we use Maxwell equations for the boundary conditions. Maxwell's equations tell us that the electric and magnetic field will be continuous at the interface of two materials. If we have these boundary conditions, then we connect the interfaces of one particular material, or let's say we connect the fields at the interfaces of one particular material through these 6 different equations that we came up with. Then we played around with these equations and wrote the equations in a matrix form, so that we had on one hand a vector that gave us the electric and magnetic field at the top interface, and on the other side of the equation we had the electric and magnetic field for the bottom interface, and then a matrix connecting these two. And this matrix only contained information about, or let's say it had only information about this material that we were interested in, and it didn't have any information of the surroundings. And now the nice thing is that we can now add, for each different material, we can add one additional matrix, and then first calculate the whole overall matrix, and then use the different matrix elements and put it into the equation where we can then calculate the transmission and reflection and absorption with. So that is how the transfer matrix method works. I can imagine not everyone was able to follow all of this now. We will actually briefly repeat it next week when we talk about photonic crystals, because we can also derive some of the photonic crystal properties from the transfer matrix method, something we're going to, as I said, talk about next week. What I should also mention is that you saw how Lisanne calculated a thin film stack consisting, I think it was 26 layers. So now you're probably wondering, if I put 26 2x2 matrices into MATLAB, my MATLAB is going to explode. Well, true, it would take you a long time to hard code this yourself. It's possible, it's not impossible, but it would take a while. And to be fair, Lisanne did not use a hard-coded MATLAB script herself. I think she would be perfectly capable to do that, but she did use a simulation software in which she, which basically optimized this whole matrix calculation. I don't exactly know how they do it, behind the scenes, but there are softwares then with which you can perform these calculations then in a very fast and smooth manner, and don't have to worry about multiplying each matrix by another. But it's of course good to still understand how this whole thing works. The reason why it's always good to understand how, let's say, the fundamentals of such a algorithm work is because then you also know the limits and you know where you can apply it and where you cannot. And and what's the cool thing is that now with the transfer matrix method, you can calculate a lot of these thin film properties for these one-dimensional stacks of multiple thin films. And There are applications in many, many fields. Of course, my own research focuses on applications for sunlight, so that's also why I presented you one of the projects that I'm currently most excited about. And the other thing that's really cool about optical simulations, contrary to a lot of other types of simulations, is that provided that you use the correct material input data, so the correct refractive index and the correct layer thickness, that's really most of the time it, your results can be predicted really well computationally, and what you then fabricate and measure in the lab normally matches what you simulated, and that's really cool. And that's why I showed you Lisanne's experimental results also to prove this statement a little bit. Okay,